Hi everyone. So in this video, we're going to get back to talking about functions, and specifically we're going to be focusing on getting different types of information by looking at the graph of a function. So this is a section in the book, section 2.3, that we'll be spending a few videos on. But this first video, we're going to be focusing on finding the domain and range of a function by looking at its graph, as well as solving inequalities graphically. So we're going to start with domain and range. And before we get into how to do that using a graph, I want to just remind you of the definition of the domain and range. So the domain of a function is the set of all inputs of the function, right? All of the different x values that you can plug into your function. And then for range, so range we haven't focused on so much. So, in previous videos, we found the domain of functions by looking at their equation and kind of using algebraic methods. So we didn't do that with range, but I did define for you what the range is. So I'll just remind you, the range of a function. So if the domain is the set of all inputs, well, then the range is the set of all outputs. Okay, so what does this translate to in terms of a graph? Well, let's start with domain. So when you're talking about the inputs of a function and you're thinking in terms of the graph, what do those inputs correspond to? Are those x values or y values? They're x values, right? The inputs are the x values. And so when we're looking for the domain of a function by looking at its graph, you're basically just looking at what are the x values that are included in this graph. So graphically, the domain is the set of all x values included in the graph. And we'll see how we can figure that out when we get to an example. And then similarly, if you are looking at the range, well, then the range is the outputs. And remember, outputs are y values when you're looking at a graph. And so instead of looking at all the x values, you're now looking at all the y values included in the graph. And by the way, when I say set, the set of all, so set is just kind of a generic word to mean like a collection of things, right? So a collection of all the x values or all the y values. What we'll see is that in the types of functions that we're focusing on in this class, the domain and range are generally going to be intervals. So we're going to be expressing them in interval notation, just like we did with in earlier videos about domain. Let me just finish the sentence, included in the graph. Okay, so we're going to do a bunch of examples. We're going to start by looking at examples where it's just a graph. There's no kind of formula given. And then we'll also do some examples where we have both the formula and the graph, so we can kind of see that, okay, our answers agree with one another. Whatever we'd get by using algebraic methods agrees with what we see by looking at the graph. But yeah, so this example is just, there's no formula involved, it's just a picture. And so we're stuck using this picture to figure out what the domain and range are. So let's start with domain. So to find the domain, we want to be looking at what are the x values that are included in this graph. And so what I would recommend is kind of like scanning from left to right. I'm just going to kind of do a squiggle here just to represent that fact. So scanning from left to right, and notice there are no x value, like none of the x values I've gone to so far are included in the graph, right? There's like no graph over here. And so where does the graph start? Well, it starts at x is equal to 1. So I was scanning along and I realized that the domain starts at x is equal to 1. And we want to use a bracket. And so I want to just remind you of the significance of this closed and open circle. The closed circle represents the fact that there is in fact a point at 1, 1. Whereas when you have an open circle like that, that's meant to indicate that there's actually no point at 3, 5. It's like everything up until that point is included, but then the point 3, 5 itself is actually not a part of the graph. And another thing, and this will come up in some later examples, is putting the closed circle is kind of optional. So if, like, let's say that the closed circle hadn't been there, it had just looked like this, then that you would also assume that that point is included. It's really just, you put the closed circle there to like really emphasize that fact. But if there's no circle at all, assume that that point is included. Okay, so we decided that the graph starts at x is equal to 1. We keep scanning along. We see graph. Okay, where does the graph stop? It stops at x is equal to 3. However, because we have a hole in the graph, we want to use parentheses because that value of x equals 3 is not actually included in the graph. Everything up until 3 is, right? Like 2.9, 2.99, 2.9999999. Every point up until 3 is included, just not 3. And that's exactly what this interval notation is telling you. Okay, so to find the range, we want to do the same thing, but now looking at y values. So we want to go bottom to top and look for, what is the first y value that is included in our graph. And so if we start down here, we're scanning along, we're like, okay, there's no graph here, right? There's no part of the graph down here. And so when do we first hit the graph? We hit it at at y is equal to 1. So in this case, they're both 1, but in this case, the 1 comes from y equaling 1. Okay, so now we're scanning along. Okay, we see the graph, we see the graph, we see the graph, we see the graph. Where does it stop? It stops at y is equal to 5. And again, because of that hole in the graph, 5 is not included. Okay, so let's do another example. And as always, I really encourage you to pause the video and try some of these yourself as we go through, because like I said, we will be doing a good number of examples. Okay, so domain, again, same idea as the last one. We want to scan left to right and kind of see like what's the first x value that's included, what's the last x value. And so what's the first x value that is included? Well, scanning left to right, we see that the graph begins at x is equal to 0. And similar to the other one, we have a closed circle, and so that means that 0 is included. And then we keep scanning, and we see, okay, where does the graph end? It ends at x is equal to 3. But just like with the last one, that point here is not included because of the hole in the graph, and so we want to put parentheses around the 3. So the domain is all numbers from from 0 to 3, not including 3. All right, now the range. And I think the range on this one is a little bit trickier. There's just kind of one thing that's a little bit funny about it. So just like before, we want to start scanning from bottom to top and see, what is the first y value that's included and what's the last y value that's included. So when we start at, scanning bottom to top, we see that the first y value that's included is y is equal to 1, right? That's the lowest y value that's included in this graph. And we have an actual point there, so we put brackets or a bracket. So now if you keep scanning upwards, so I'm going to again just kind of draw this to represent the fact we're moving along, you might notice something a little funny happens at 4. So at a height of 4, there is this hole in the graph. However, there's also a point here, and it's not like shaded in, but here there's a point, right? There's no hole in the graph at this point here. And so that means that the y value of 4 is included in the graph. Now, if there had also been a hole here, if these were like both holes, well, then 4 would not be included, and you would actually have to write this in as 2 separate intervals. It would be like from 1 to 4 and then from 4 to 5. But because there's no hole in the graph here, 4 is still included. This hole here is kind of a false alarm. And so we keep going, and what is the last y value that's included? Well, it's 5. And now should we include 5? So should we put a bracket or should we put a parenthesis? Well, remember what I mentioned earlier, unless there's a hole in the graph, you want to assume that that point is included. So it's not like a point is only included when there's a circle drawn on it, right? All these other points in the graph, all along the graph, are all included, and that includes this point here. So it's as if this had, a point on it. It doesn't need to have the point there to signify the fact that it's included. And so we put a bracket around 5. Okay, So those are two examples that were kind of just from a graph. These next few we're going to do are going to be ones where I want to talk about how, what the domain would be just by looking at the equation, and then also kind of confirm that that agrees with what we get when we look at the graph. So this is the function f of x is equal to x squared minus 6x plus 8. So maybe pause for a moment and think what, forgetting about the graph, what would you say the domain is based on what we learned about domain in previous videos? So we learned that basically the only reasons that a function will have issues in its domain is if you're taking the square root of a negative number or if you're dividing by 0. And so remember we said that if you have a function that doesn't have any variables in the denominator, doesn't have any square roots, the domain is just going to be all real numbers. And so the domain should be all real numbers, which would be negative infinity to positive infinity. And we'll see that that is true. But there's one kind of thing you have to be aware of about this graph. So notice that this graph kind of just goes up to the edges of the page. Whenever that happens, you want to assume that the graph continues. If the graph is not supposed to continue off the page, they'll always do something like put a circle there or put a hole, something to be like, okay, that's the end of the graph. If it just kind of keeps going off the page, assume that that means it keeps going. So if you want, you can put arrows on it, but I just want you to know that I'm not always going to put arrows on the ends of graphs. You have to be aware that they do keep going if they just kind of, go off the page. Okay, so again, the domain is supposed to be all of the x values that are included in this graph. And so, we don't have the whole graph here, right? We know that the graph keeps going off the page. And so, without looking at the whole graph, knowing the fact that it keeps going, right? It keeps going this way, it keeps going this way, it's eventually going to reach all x values this way and all x values that way. It's not going to get there very quickly, right? There's going to be, you have to go like really far up to see the really small or really big x values, but they are a part of the graph. So the domain is in fact negative infinity to positive infinity, which is what we guessed based on the formula. Okay, so now talking about range. So range is something that we were not able to do based on just the equation in the past. So this is where, having the graph is really helpful. So for the range, again, we want to look bottom to top and just see, what are the values that are included. So notice that the graph just doesn't exist down here, right? There's no graph below -1. And so the very first value in the range is going to be -1. And then if we keep scanning upward, we can see that the graph just keeps going and going, right? We have this arrow, we know that the graph is going to keep going off the page, it's going to keep going up and up and up. And so there is no upper bound of the range. The range is going to go up to positive infinity. Okay, so we're going to look at another example, kind of similar, kind of different. So once again, this doesn't have arrows on it, but we can assume that it keeps, let's see if this is a better match for the color. Yeah, we can see that it keeps going in both directions. Okay, so let's look at the equation. So the equation here, g of x is equal to x cubed minus 4x squared plus 2x plus 3. That is similar to the last one, right? There's nothing that could go wrong, so we should expect that the domain is all real numbers. And just like the last one, we cannot see for ourselves that all x values are included in this graph, but because the graph keeps going to the left and it keeps going to the right, I know it looks really steep. It almost looks like it's not going to reach these, bigger x values, but it does. It just takes a while to get there because it's such a steep graph. But the domain is still negative to positive infinity. Okay, what about the range? So the range on this one, if we scan from bottom to top, notice that because we have this arrow on the bottom, the graph just keeps going down. So the bottom end of the range is negative infinity. And then if we kind of scan upward, 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 we see that the graph actually just keeps going, right? It never stops. And so the top end of the range is positive infinity. So in this case, the domain and range are both all real numbers. But I just wanted to kind of compare and contrast the last one and this one because, it's very possible for there to be two different functions where both of them have a domain of all real numbers, but not both of them have a range of all real numbers. So it really depends on the graph shape, right? If you have a graph like this one, a parabola, where it faces one way, right? It points upward. Well, that means that you're going to have a lowest point in your graph. Whereas if you have a graph that's shaped like this one, well, it points up and it points down. So it's going to cover all real numbers as a result of that. Okay, so I want to look at another example, and actually let me erase this off here. So this is the function, and actually I need a little bit more space. Let me just move some of these things down because we're going to, this next example is kind of an important one. So we're going to write some extra information about it. Sorry, there we go. Okay, so this is the function f of x is equal to the square root of 9 minus x squared. So this is a good example of a graph where, if you just go and graph it in Desmos, it's going to look exactly like what I pictured here. So it's not going to include like closed circles at the endpoints. But again, you can assume that that means that the points at 3 and -3 are included. So if you want, you can add those in yourself just to really emphasize that fact, but it's not necessary. It's only necessary to put a symbol if the point is excluded. Okay, so this function should be kind of familiar. We've dealt with this function in previous videos about finding domain. We actually did this exact example, and I'm not going to go through it, but I would encourage you to pause. I think this would be a great time to just review how to find the domain of this function algebraically. So yeah, I'm not going to go over it, but I would definitely recommend pausing and trying it. And then you can always go back to, it was the video where it was called like finding the domain of a function. So the domain of this function we found in that previous video was all numbers from -3 to +3. And that agrees with what we see here, right? Scanning left to right, we can see that the domain is -3 to +3, including both the -3 and the +3. And then what about the range? Well, if we scan from bottom to top, we can see that the very first y value that's included is 0, right? There's nothing below 0. And then if we scan upward, we see that the very last y value that's included is 3. And 3 is included, right, because there is actually, the graph does go through a height of 3. And so the range is from 0 to 3. So what kind of a shape is this graph? I want to kind of make a connection between this function that we're looking at here with what we talked about actually in the last video. So how would you describe the shape of this graph? It's not really a parabola, right? It's a different kind of a shape. So this graph is actually a semicircle. It's half of a circle. And I want to kind of dig into like why that is. Why is it that this graph looks kind of like a circle? So note, f of x is equal to the square root of 9 minus x squared is a semicircle. So the word semicircle basically just means, again, half of a circle. And which half is it specifically? Like imagine if I kind of completed this circle, it's the top half, right? And we'll talk about what the bottom half would look like in terms of the equation in a moment. So what would the equation be of this full circle? So I just kind of sketched it roughly. What would the equation of this circle be? Well, based on the previous video, we learned that when you have a graph with a circle with a certain center and a certain radius, you can write its equation. And so if you have a circle specifically with a center of 0, 0, that means that, so let me just make a note of this. So the whole circle equation would be x squared plus y squared, right? So why is it just x squared plus y squared? Well, because the center is 0, 0, you would not be adding or subtracting anything from x and y, right? The circle has a center of 0, 0. And then what would the right-hand side be? It would be the radius squared. And the radius squared is 9 because the radius is 3. So how could you kind of relate this equation for the whole circle to this equation for the semicircle? Well, let's see what happens if you try to solve this equation here for the circle for y. So if you wanted to solve this for y, you would want to subtract x squared from both sides, right? So you would have y squared is equal to 9 minus x squared. And then you would want to take the square root of both sides. But there's kind of like one more thing that we need to write down here. So actually, let me not write that step out. I'm going to kind of jump to another step. So basically, and I don't want to spend too much time going into exactly why this is, but if you have something like this where you have y squared is equal to something else, remember that means that y could be positive or negative. So when we take the square root of both sides, we would actually get plus or minus the square root of 9 minus x squared. I know it's maybe a little complicated to understand because we have a lot of different letters and numbers going on here, but just think about, like, just as a total side example, if someone asked you to solve y squared is equal to 16, the answer wouldn't just be y is 4, it would be y is plus or minus 4, right? Because you can take either a positive or negative number and square it to get 16. And so similarly here, if you have y squared is equal to, whatever this number is, well, just saying square root, that would be a positive answer. You need to also include the possibility that y could have been a negative result. So what did we do? We basically started with the equation for a circle of radius 3 centered at 0, 0, and we kind of rewrote it a different way. So at this point, what you can do is you can split this into two different equations. So one of them would be, you could write y is equal to, or f of x is equal to, the square root of 9 minus x squared. Or you could have f of x is equal to the square root of, the negative square root of 9 minus x squared. And so what's the significance of these two different pieces? Well, one of them is the top half of the circle and one of them is the bottom half. So this first one is the top half of a circle because it's positive, right? It's going to always give you positive outputs. This one, because there's a negative sign on the outside, is always going to give you negative outputs. So this is the bottom half of the circle. So I just wanted to show this to you because this is a shape that will come up probably a little bit more in this class and then definitely will come up in calculus, especially calculus 2. This kind of a graph where you have f of x is equal to the square root of some number minus x squared. That's always going to give you a semicircle. And specifically, if it doesn't have a negative sign on the outside, it's going to be the top half of a semicircle. So hopefully you can see, even if you didn't quite follow all the details of this stuff, the main thing I want you to understand is, that there's some relationship, right, between this equation and this equation. I hope that you can see that in some ways they're kind of saying the same thing. Okay, so that was an equation of the form square root of 9 minus x squared. You might remember that we also did some problems where it was kind of reversed. So this is actually the graph of the square root of x squared minus 9. And so if you go back and look at the video where we did this example, instead of getting one interval, instead of getting all the numbers between -3 and 3, we got two different intervals. Our answer was all the numbers less than -3, and then also all the numbers greater than +3. And we can see that this graph tells us the same thing. So again, it doesn't have these points here, but we can add them in here. And so the domain of this graph, and actually this also continues, right? So the domain of this graph is going to be -∞ to -3, including -3. And then it's also going to be everything from 3 to infinity. And so again, I'm not going to go back over how to do this, but I really encourage you to remind yourself how the algebra works, because I think one of the things that's most important to me when I teach is to show you kind of multiple ways of understanding something. So I think it's really great if you can understand the algebra of where the domain comes from on this example, and then how that's different from the previous example. And then I think it's really cool to be able to confirm, okay, well, the domain actually is different for these two. And we can see that in the graph. We can see that when you have 9 minus x squared, we get this like one kind of piece of a graph. So the domain is just one interval. Whereas in this example, if you graph it, you get two different pieces of the graph. And so instead of just being one interval, the domain is two different intervals. Okay, so next up we have the range. And so the range in this case starts at 0, right? That's the smallest y value that's included, and it is in fact included in the graph. And then it just keeps going up and up and up. And so the range goes all the way up towards infinity. And I'm not going to talk about this in this video, but I think it would be interesting for you to take a minute to compare the range for these two, and without looking at the graph, maybe look at this equation, and try to figure out why is it that one of them has a range that's 0 to infinity and one of them has a range that is just 0 to 3. And I would remind you that the range is the set of all possible outputs. So if you're trying to figure out the range by looking at the formula, which we didn't really do, but I think it's just interesting to think about, you should really be thinking about, what kind of numbers are allowed to come out of this function. So leave that at that. Okay, we're going to look at one more example. Just to show you one more example that we actually did in the video that we can now confirm. So this was f of x is equal to x squared plus 1 over x squared minus 4. So on this one, we're just going to talk about the domain. The range is a little tricky to determine from this graph because it's hard to see the exact values. But yeah, so this one we did in, again, that same video where we found domains of different functions. And basically what we did is, remember, we factored the denominator, right? We found that the denominator can be written as x plus 2 times x minus 2. And so what we figured out is that the domain was all real numbers except for positive and negative 2, because those would be the numbers that make this denominator equal 0. And so I just wanted to show you how that looks in this graph. And this is a topic we'll actually get a lot more into towards the end of the quarter. So this is a graph that has a feature that's called a vertical asymptote. So a vertical asymptote is basically when the graph kind of does this thing where, like, see how this side kind of goes up and this side goes down. And notice that one half of the graph goes up, one half of the graph goes down, but they never actually touch an x value of negative 2, right? The graph kind of like skates along a value of negative 2, but it never actually touches it. And so that's how we can tell from the graph that negative 2 is not actually part of the domain, right? Because there's this kind of split in the graph that happens at negative 2. And then we can see that the same thing happens at positive 2. The graph also kind of has this split, right? It doesn't actually touch an x value of positive 2. And so just like we saw in the other video using algebra, from this graph we can also tell that the domain is going to be negative infinity up until negative 2. So, right, like everything is fine up until negative 2. At that point, we have an issue in the graph. And then it's everything from negative 2 to 2, right? This part is fine. It's just negative 2 and 2 that are issues. And then the last portion of the graph is everything from 2 onward, not including 2. And so really the only issues, like we said, are at negative 2 and 2. So yeah, I'm not going to talk about the range on this one, like I said, but I just think these last few examples, I just wanted to kind of show you that everything we found in the videos using algebra, those same answers hold true when we actually look at the graph. And so that's something you can always do to kind of check your answer when finding the domain, is go ahead and graph it. That being said, on like a test or a quiz, if I'm asking you to find the domain using algebra, you do need to know how to use the algebraic methods as well. You need to know kind of both methods. Okay, so that is pretty much it for finding the domain. We'll do one more example at the end that kind of brings everything together. The next thing I want to talk about is solving inequalities graphically. And we're actually going to start by just refreshing on what it means to solve an equation graphically, which is something that we did do some examples of, like at the very beginning of the quarter. So this is the function, so the equation of this function is f of x is equal to, I think same one actually from before, x squared minus 6x plus 8. It's just a nice example for this purpose. So I want to start by, like I said, doing some questions that we've already done in the past. So this is kind of review. So first thing I want to do is using the graph, not using any algebra or solving equations, using algebraic methods. I want to figure out how could we solve x squared minus 6x plus 8 is equal to 0. What does that mean? What does it mean to solve an equation just by looking at the graph? Well, because our function is x squared minus 6x plus 8, what I just wrote down here, you could also phrase this as find all values of x such that f of x is equal to 0, right? That means the same thing. Solving x squared minus 6x plus 8 equals 0 is the same thing as finding all values of x such that f of x is equal to 0. So how do you do that graphically? Well, you just go and you look at the graph and you look at what are the x values that give you a y value of 0, right? Because when we talk about f of x equaling 0, that means that the y coordinate should be 0. And so where are those points? Well, we can see those points happening here and here, right? Those are the points where the y coordinate is 0. And so our answer would be x is equal to 2 and x is equal to 4. Because when x is 2, y is 0, and when x is 4, y is 0. How could you check those answers? So you could check them by plugging these x values into the function, right? Because any point that is a solution, when you plug it back into the function, you should get the right answer, right? So if we plug in x is equal to 2, and I would encourage you to try this yourself, you should get 0. And if you plug in x is equal to 4, you should also get 0. But we don't need to do that, right? We can do it just by looking at the graph. So similarly, let's do one more kind of along these lines. So let's solve now x squared minus 6x plus 8 is equal to 3. So now we're trying to figure out what are the x values of the points where y is equal to 3, right? Because this is our function. This is f of x. So I'm not going to rewrite that orange statement, but it's the same idea. So now we're looking for all values of x such that f of x, the y value, is equal to 3. And so now we want to go and look at a height of 3 and see what are the points on the graph that occur at a height of 3. And we have these 2 points here. And so those solutions are going to be x is equal to 1 and x is equal to 5, right? Those two are the x values that give you a y value of 3. And again, how could you check that answer? Well, and I would really encourage you to do this just to really demonstrate it to yourself. If you plug in x is equal to 1 into this equation, you should get 3. And same thing should happen if you plug in 5. Okay, so that's how it works for solving an equation, right? So anytime you're solving an equation, you're trying to find the values of x that give you the y value that you're looking for. And so we'll see that solving inequalities is basically the same exact idea. Okay, so now we're going to solve inequalities. So the next example we're going to do is we're going to now solve the inequality x squared minus 6x plus 8 is less than or equal to 3. So first let's kind of translate that. What are we going to be looking for on the graph? We're basically going to be trying to find all values of x such that f of x, because f of x is the same as the function on the left side, is less than or equal to 3. And just like before, remember when we said if f of x equals 0, if this equation equals 0, that's always referring to a y value, right? So when we're talking about f of x being less than or equal to 3, that means that we should be looking at the parts of the graph where y is less than or equal to 3. Right? Because f of x is the y values. And so what we want to do is go onto this graph and look at what is the part of the graph that lies below a y value of 3. So here's when y is equal to 3. Here's when y is equal to 3. So let's shade in the part of the graph where the y values are below 3. So the y values are below 3 on this part of the graph, right? This is the part of the graph where the y values are below 3. Anything up here, the y values are over 3. Okay, so how do we express that? How do we write that down? Well, that's an interval, right? It's all of the x values. Remember, our answer should be x values. We're looking at y values to find the answer, but our answer needs to be x values. And so what are the x values that are included in this part of the graph? Well, it's all of the x values from 1 to 5, right? Any x value between 1 and 5, we can see that the graph lies below 3. And so our answer is going to be the interval from 1 to 5, right? Because that is the part of the graph where that lies below a height of 3. Okay, let's do a similar example, just kind of swap something. So instead here, and maybe let me do a different color so it's easy to kind of look between them. So now let's solve x squared minus 6x plus 8 is greater than or equal to 3. So we're basically doing kind of the opposite thing now. So now we're going to this graph. Here again is where it equals 3. Now we're looking for where are the y values above 3. Right, so I'm not going to write down this orange sentence again, but it's the same idea. Find all values of x such that the y values, such that f of x is now greater than or equal to 3. So we need to highlight the part of the graph that lies above a y value of 3. So that's going to happen here, right, and here. These are the parts of the graph that lie above a height of 3. Everything down here lies below a height of 3. Might be helpful when you do this, by the way, I didn't do this, but to draw like a line at whatever height you're talking about, right? This is our height of 3. We're looking for what lies above and below that line. Okay, so how do we write down this part of the graph we just shaded? Well, in this case, it's going to be 2 intervals, right? It's everything up to and including 1, because the graph keeps going this way, it keeps going up. And then it's going to be everything from 5 onward, right? Keeps going up this way too. And so our answer is going to be negative infinity up until 1, including 1. And then remember, this union symbol means and. And then we also have everything from 5 onward, right? That's also the part of the graph that has that lies above a height of 3. All right, let's do a couple more with this same graph. And I know this video is probably getting a little long, but we'll do a couple more examples with this graph. And then the last thing is going to be just like another example of just practicing everything. So you're welcome to, if you start to feel like you really know how to do this stuff, you don't need to do the last example together. Okay, last one I want to do with this. So now let's solve x squared minus 6x plus 8 is greater than 0. So now, instead of finding which part of the graph lies above or below 3, now we're looking for which part of the graph lies above 0 specifically. So we want to go to 0, and so a height of 0 would be here, right? And we want to look at what is the part of the graph that lies above, and let me use a different color because this blue is going to blend right in. So we're looking for what is the part of the graph that lies above 0. And so it's all of this part here, right? This all lies above 0. And this part here. There's one difference though, right, with the other example we did, other than the fact that, this one was 3 and this one's 0. So what's the difference? Well, in this case, notice there's no equal sign here. So we're looking for the graph not to equal 0, but to be strictly above 0. And so what is the difference? Well, that tells us that we actually don't want to include these 2 points, right? When x is 2 and when x is 4, the function equals 0, and we don't want that. We want the graph to be strictly above 0. And so our intervals are going to have parentheses instead of having brackets because of that. And so the first interval is going to be negative infinity up until 2, but not including 2. And so we're going to put a parenthesis. And then the second interval is going to be 4 to infinity with a parenthesis, because when x equals 4, the function equals 0. And we don't want that. We want the function to be greater than 0. So basically, what's kind of the shortcut to knowing whether there's going to be parentheses or brackets, it has to do with whether your inequality has a equal sign as part of it or not. So I'm not going to do this example, but if instead we did, x squared minus 6x plus 8 is less than 0, that would also involve parentheses instead of brackets because there's no equal sign. Or if you had gone back and switched, if we took these two examples that we did earlier, and if we just changed them by getting rid of the equal sign, all that would change is that these would become parentheses because we're no longer including those kind of like transition points. Okay, so one last thing we're going to do, and let me just finish erasing that extra stuff. So last example we're going to do is just look at one last graph and do both finding the domain and range and solving a couple of inequalities. So this is one where we don't have an equation for the graph. So this is just some random function that is a kind of a mystery function. Maybe let's call it g of x. Okay, so first thing we want to do is we want to find the domain and range of g of x. So I'd encourage you to pause and try this as well as the next examples yourself. Okay, so what is the domain? Well, we can see that the graph kind of keeps going off of the page, right? And so that means that even though we can only see part of the graph, it does continue onward to the left and to the right. And so our domain is going to be all real numbers. All right, what about the range? So the range, if we kind of scan from, again, from bottom to top, we can see that there is no lowest value on the graph, right? The graph keeps going down. And so the bottom of the graph is going to be negative infinity. However, the graph does not keep going up forever, right? If we're kind of scanning from the bottom to the top, the graph stops at 3. It doesn't continue after 3. And so it tells us that the right side of the range should be 3 with a bracket because this point is included in the graph. Okay, so now we're going to solve a couple of inequalities. And this is going to look a little bit different from what it looked like in the last one, but it's going to be pretty much equivalent. So let's start by solving f of x is less than or equal to 0. So what's different about this compared to the last one? Well, for the last one, we actually knew the equation of the function, right? And so instead of writing f of x is less than or equal to, I actually just wrote the equation of the function is less than or equal to 3 or whatever we are solving. And so this is the exact same idea. It's just that we don't have the equation. And so that's why we're just writing f of x, or I guess I should say g of x is the name of our function. Okay, so how do we solve g of x is less than or equal to 0? We want to look, so we can go and draw a line at a height of 0 and say, okay, so we're looking for the parts of the graph that lie at or below 0. And the reason I said at is because we do have this equal sign. So we want to include the points where it equals 0. So we have this point, but then we also have everything below. So this stuff down here. We have this point, then we have all of this stuff that lies below. We have this point where it equals 0. We have this point, and then we also have everything below. And so we're actually going to have 3 intervals. So what is the first interval going to be? It's going to be negative infinity up until 3. And we're going to include 3 because we did want to include the possibility that the function equaled 0. And then the next interval, and sorry, that's a negative 3, my bad. And then the next interval is negative 1 up to 1, including -1 and 1, because that's where the function actually equals 0. And then the final interval is everything from 3 onward. So 3 to infinity, again, including 3. All right, one last thing to answer about this one. So now let's solve g of x is greater than, not greater than equal to, greater than 0. So now we're looking for the parts of the graph that lie strictly above the x-axis, above a height of 0. And so that means we're looking at this part of the graph here, and we're looking at this part of the graph here. And then we're not going to include these points, right? Because these are the points where it actually equals 0, and we don't have an equal sign in our inequality. And so what are the x values of those parts of the graph we shaded in? Well, they're everything from -3 to 1, not including, or sorry, -1, I keep forgetting the negative signs, not including -3 or -1. And then it's everything from 1 to 3, not including 1 and 3. All right, I will see you all in the next video where we'll be talking about a couple of other kind of pieces of information that you can get by looking at the graph of a function. So I'll see you then.